In the last example, we saw this series of 1 over the square root of n plus 1, and we thought that the value of 1 over the square root of n plus 1, this guy should be pretty close to the value of 1 over square root of n. However, if we try to use the comparison test, it turns out that, well, because 1 over square root of n is bigger than or equal to the 1 over the square root of n plus 1, so this guy is going to be bigger than this guy. However, because my right hand side, this guy diverges. So we can't really conclude anything about the value about whether or not my left hand side converges or diverges. But we expect that, well, the value should be pretty close. So this guy, maybe it should diverge as well. But we can conclude that using the comparison test. So we can use another test. This one is called limit comparison test, and how this works is that when we have another series to compare with the original series, we can compute the limit of the ratio between the terms of the two series. We can compute the limit of an over bn, where my n goes to infinity. If this limit turns out to be non-zero real number, so this is important, it has to be non-zero, it cannot be zero, and it has to be a real number. It cannot be infinity or negative infinity. It can be any number. It can be 1 to negative pi. It can be 100, 1,000, whatever, as long as it's non-zero and it is a real number. Then the series an and bn will have the same convergence and divergence status. So if one of them diverge, the other one is also going to diverge. If one of them converge, then the other one is going to converge as well. So if we try to use the limit comparison test with this one, so I'm going to use limit comparison test with 1 over the square root of n. Then I can compute the limit of the ratio of the two terms of the series. So I'm going to compute the limit when my n goes to infinity of 1 over the square root of n over 1 over square root of n plus 1. So here, this should be in the sum. So I'm going to compare with the series 1 over square root of n, where my n goes from 1 to infinity. So here I'm comparing the limit of the ratio of the terms of the two series. Okay, so this is what I am computing. Now let's try to find out what this guy is going to be. So this is going to be the limit when n goes to infinity. I'm going to bring the denominator up, so I'm going to get the square root of n plus 1 over square root of n, and this is going to be just the limit when n goes to infinity of 1 plus 1 over square root of n. And when my n get really large, 1 over square root of n is going to get really small. So this limit is going to be just 1 over 0, which is just 1. 1 plus 0 is just 1. So this limit turns out to be a non-zero real number. So this works. So that means these two series is going to have the same convergence or divergence status. And because we knew 1 over the square root of n, this guy is a p-series. So let's see. Because this guy is a p-series with p equal to 1/2. So we know it is going to diverge. So now then we can conclude that the series that we have in the question here is also going to diverge. So this guy would diverge. Okay, here we go. So let's take a look at the next one. The next one I would like to see if this series converges or diverge. So again, to use the limit comparison test, I'm going to have to find another limit to compare this series with. So I'm going to use limit comparison test with something. So now again, the big question when using the limit comparison test with what series am I going to compare with the original series? And as you can see, if you look at the original series, I have 2n cubed minus n squared plus 5 over n to the 7 plus 6n to the 4th minus 1. If n gets really large, the value of 2n cubed is going to be a lot larger than n squared. Is going to be definitely a lot bigger than 5. And same with the denominator. The value of n to the 7 is going to be a lot bigger than 6n to the 4th, and also it's going to be a lot bigger than 1. So it seems like the leading term is going to dominate the other two terms. So maybe I can compare this series with this one. So I'm going to look at the sum when n goes from 1 to infinity of just 2n cubed over n to the 7. So I'm just going to look at the leading term in my series here. And if I were to use the limit comparison test, that means I'm going to have to compute the ratio of the terms between the two series. So I'm going to compute the limit of, let me see. Well, by the way, this guy, if I were to simplify this out a bit, this is going to be just the sum of 2 over n to the 4th. So this is going to be, I'm going to use here. This is going to be what I'm going to use here. So I'm going to have, let's see, 2 over n to the 4th over the original series, which is 2n cubed minus n squared plus 5 over, let's see, n to the 7 plus 6n to the 4th minus 1. So once again, it's just a ratio of the terms in the new series and the terms in the original series. By the way, when we compute this ratio, it can be anything divided by anything, by the way. So I can flip these two terms here and it would not make a difference. I can put the pink term in the numerator and put the blue term here in the denominator, and that would not change the result of the test. So if I were to compute this guy, this is going to be just the limit when n goes to infinity. I bring the pink term to the numerator, and that is going to give me a ratio of, let's see, I'm gonna have 2 times n to the 7 plus 6n to the 4th minus 1 over n to the 4th times, let's see, 2n cubed minus n squared plus 5. And this is going to be the limit when n goes to infinity of 2n to the 7 plus 12n to the 4th minus 2 divided by 2n to the 7 minus n to the 6th plus 5n to the 4th. Okay. Now then, when we have the limit of a ratio of polynomial, we can just compare the leading term of the polynomial. So this is going to be just 1. And the reason why it works this way is that I can divide both the numerator and the denominator by n to the 7. If I do that, let me try to do this here real quick. This whole thing divided by n to the 7 divided by the same thing plus 5n to the 4th over n to the 7. Notice how the value of the thing behind the limit here doesn't change because I divide n to the 7 to both numerator and the denominator. And it turns out that this limit is going to just equal to the limit when n goes to infinity of, let's see, 2 plus 12 over n to the 3rd minus 2 over n to the 7. This whole thing over 2 minus 1 over n plus 5 over n cubed. And when n gets really large, this whole thing, 12 over n cubed, is going to be 0, 2 over n to the 7 is going to be 0, 1 over n, 5 over n cubed. These are going to be 0, so I'm going to end up only with 2 over 2, and that's going to be just 1. So that means this limit works because it is a non-zero real number. So then that means this series here is going to have the same convergence and divergence status as this other series. And now then, if we take a look at this series, this is a P series. Well, actually I can pull the two out, just to be sure. I can pull the 2 out, and that is going to be 2 times the sum of 1 over n to the 4 when n goes from 1 to infinity. And now this guy is a p-series with p equal to 4. So we knew that a p-series when p equal to 4 is going to diverge, and multiplying by a constant 2 doesn't change that fact. So that means this guy converges. So this guy converges. So that means the original series that we have is going to also converge. It's also going to converge. So this is how the limit comparison test works. So once again, we have to find another series to compare with the original series, and the way it works is that I compute the limit of the 2 terms of the series. If it turns out to be a non-zero real number, then these 2 series is going to have the same convergence and divergence status.